Hi everybody, welcome back. We're going to continue our discussion about waves today, and we're going to look at a few more wave properties. Or characteristics. The ones specifically that we're going to look at is a property called the frequency of a wave. And we're also going to look at something called the period of a wave. And we're going to look at the speed of a wave, the speed at which the wave travels. So first of all, we'll begin with frequency. The word frequency in English, right, the frequency of something describes how often it happens. And it's basically the same thing for a wave. If I draw an axis here, and underneath it I draw another one so we can compare. If we consider this to be time passing along this horizontal axis, right, and remember the displacement of the wave along the y-axis, here in red I'm going to draw a wave. So this wave would trace out as you vibrate an object up and down as time goes on. It would trace out something like that. And on the bottom one, I'm going to draw an object that is vibrating more quickly. Instead of a slow vibration, it's vibrating up and down much more quickly. Okay? So these two waves are obviously different. I tried to draw them with about the same amplitude. The amplitude is the height of the wave, or the amount of displacement, remember. But now what I want you to do is I want you to focus on one full cycle, one wavelength. So if I draw a line right here, then I'll draw it all the way down here so you can compare it to the other graph. For the red wave, you can see that what we have here is one wavelength. Remember what a wavelength is. It's the length of the repeating unit of the wave. Once you get to the end of this section, you kind of start over and create a whole new wave, or a whole new vibration. So this is the wavelength of this wave. And this little time t here is the amount of time it takes for that wavelength to occur. But if you look at the blue wave, one wavelength is really only this much time. There's one full cycle of the blue wave. In other words, the blue wave does more than one cycle in the same amount of time. There is more than one wavelength, or more than one vibration in the same amount of time. And so we say that the blue wave has a higher frequency because the occurrence of waves happens in a shorter time. You could say it happens faster. So this is what we mean by a higher frequency wave, and the red wave has a lower frequency. A wavelength occurs in a shorter amount of time for the blue wave. So, mathematically, we can express the frequency as the number of vibrations per second. How many vibrations would you get in a unit of time, say a second? So it's the number of vibrations or oscillations, both words could work there, in 1 second. We sometimes call the number of oscillations cycles, right? If you go from your, if I go back to the red wave here, if we start in this position, we vibrate up, then we vibrate down to the lowest point, and then back up again. And that's where we would start over, right here, up, down, up. That's one cycle, one full cycle. So we often call that cycles. The number of cycles in 1 second, which in short can be written as cycles per second. So cycles per second is the unit that we use to describe frequency. Frequency is not an actual you'll notice the top of the fraction, it's not an actual unit as such, it's more of a counter. It's counting how many times something happens in a second. And there's no specific unit on top, because whatever you're counting could change. You could have the frequency of a ball bouncing. It could be how many times the ball bounces per second, in which case you'd be measuring some sort of position of the ball. But you could have the frequency at which I use the word the in this video, how many times the word the pops up. You could have anything that you could measure the frequency of. So frequency is an interesting unit in that the top can be just about anything you want. Now, this is a little bit complicated, not really super complicated, but we give it a special name like we do with many of the units in physics. And so we honor a fellow by the name of Hertz. And so we say a capital HZ, small z, Hertz. Okay. Actually, I think it might be yeah, I think that's good. I'm trying to think if it was a capital H or a small h, but I don't think a small h. Pretty sure you would use a capital H on that. So capital H and a Z represents hertz. And a hertz is just another way of saying 1 cycle per second. So imagine that someone is waving their hand. Here, I'll draw a little hand. And the hand is waving up and down. So I'll draw the other. Right? If the hand is flapping, waving up and down, and if you waved 6 times in 1 second, if you waved 6 times in 1 second, you would say that the frequency of your wave is 6 cycles per second. Frequency, let's try to spell things right again. The frequency equals 6 cycles per second, or you could simply say 6 hertz. A hertz is how many cycles per second. If you waved your hand slower and you only waved it 2 times in a second, then you could say it was 2 hertz. So that's what frequency means. Another way of picturing frequency is to look at a wave. I'll draw 2 waves again. Our red wave. Let's say this wave was moving this way towards you, and you were standing here. This is where you'll be. And then our blue wave, I'll put the blue one underneath. Another way of thinking about frequency is if you were standing here and these waves were moving towards you, how often would you get hit by one of the crests? In the red wave, you could see that you would get hit by a crest and it would be slower. 1 crest, 2 crests, 3 crests. Picture a wave in the ocean. How many times would you bob upwards, right, in a second? But with the blue one, the waves are coming more sort of quickly, the crests, so you would feel crest, 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 which is a faster frequency. So you can kind of visualize it that way as well. So that's what we mean by the frequency of a wave. Okay? The rate at which an entire wave passes by. That's another way to think. Okay, then what is period, which is the next thing on the list? Period is basically just the opposite of frequency, sort of. Period is used to describe the time for 1 cycle. So if you notice, there's a similarity here. We've got frequency, which is usually a small f, not a capital F, which stands for force. Frequency, we usually use a small f. Or, in fact, there are other symbols that they use for frequency as well. You'll sometimes see some Greek letters being used, but for us, we're going to just use a small f to keep it simple. So if frequency is the number of cycles for 1 second, then period is the time it takes for 1 cycle. So it's kind of just another way of looking at frequency, isn't it? It's really the same thing, just looking at it a different way. So if we go back to our 2 pictures and look at the 2 graphs, let's just say that this green line represents 1 second right here, this green dotted line. Well then, the first wave is 1 vibration per second. The red wave has only 1 complete vibration in that time. So we would say that the frequency of the red wave was 1 hertz, 1 vibration per second. But we could also say that the time it takes, the period, now period is a capital T because it's a time, but it's a special time. So not a small t for any old regular time, but a very special kind of time, capital T. The period of that wave is also 1 second because it takes 1 second for 1 vibration to happen. For the blue wave, however, let's look at how many vibrations we got in there. To keep it simple, I'm just going to pretend that that's right on the dot there, right on the line. So we've got nearly 1, 2, 3. We've been able to squeeze 3 vibrations into 1 second of time. So the frequency here would be 3 hertz. 3. I'll put a little cross there so you can tell that that's a Z and not a 2. All right? So 3 hertz, or 3 vibrations, 3 wavelengths every second. Now what about the period of this wave? Well, the period would be the time for 1 second. Or sorry, for 1 vibration. Remember, the green is 1 second. So if that's 1 second, we need to know how much that is. Well, it's pretty obvious that you're dividing it into 3 pieces, right? So there are 3 vibrations in a second, which means one of those vibrations must take 1/3 of a second. So the period is 1/3 of a second, or 0.333333 seconds. But notice right here an interesting thing. The period is really just the upside down reciprocal of the frequency. If the frequency is 3 hertz, that means you have 3 wavelengths in a second, which means that each one is 1/3 of a second. So we can describe period, the time for 1 cycle, and we can describe frequency, cycle per second, and we realize that frequency is equal to the reciprocal of period. Okay? And I guess I led you astray with this P here. We were just kind of writing stuff down. The actual symbol for period is a capital T, so we should fix that, capital T. All right? And then if the frequency is 1 over the period is also 1 over the frequency. So if you know one, you automatically know the other. And to be honest, we don't really use the period of a wave very often in physics. It's an interesting way of looking at it. It's another way of describing the frequency, but the frequency itself is usually far more important. So that's those 2 particular concepts. The last thing we should talk about for today is the speed of a wave. So we have to be very careful that we understand what we mean by the speed of a wave. So what I want to do is remind you that, we had talked about an object oscillating back and forth. Here's an object, and it would be bouncing back and forth, back and forth, back and forth, back and forth, up and down, up and down. And that oscillating object could be a ball bouncing, or it could be molecules in a bunch of water as the wave travels through. It could be humans in a sporting arena standing up and down, making a wave. And we said that what would happen is as they moved, as you graph this over time, you would see the person go up and down, up and down, and up and down. And this bubble, this crest, would travel this way. And we said that the wave would propagate in this direction. Remember? Propagate. The wave, the phenomenon. So if you're doing a wave in the sporting arena, the speed at which the sort of wave effect ripples through the crowd. And we called this over here the oscillation direction. Okay. Now what's interesting is, what do we mean by the speed of a wave? Are we talking about the speed of the oscillation, or are we talking about the propagation? Well, let's think about this. The speed of the oscillation is actually more closely related to the frequency of the wave. The faster you oscillate, the more crests you will create in a smaller amount of time. If I oscillate like this, very slowly, up and down and up and down, the wave I will create will be up and down and up and down. But if I go fast, up and down, up and down, up and down, up and down, I get a wave that's up and down, up and down, up and down, up and down, up and down. So the speed of the oscillation is really more related to how many crests you create in a second, how many wavelengths you create in a second. And so that would be more related to the frequency. So that is not what we're talking about when we talk about the speed of the wave. What we're really talking about is the speed the wave propagates. So when we talk about the speed of the wave, it's the speed of propagation, how fast the wave itself travels or ripples through the medium. And what you'll find is that the speed of the oscillation has nothing to do with how fast the wave travels sideways or propagates. What does determine that speed is the nature of the medium. The speed of propagation, the speed of the wave traveling through the medium, depends entirely on the properties of the medium. Entirely, T-I-R-E, entirely on the properties of the medium. Now, what do we mean by the properties of the medium? Well, there are many things in a medium that can determine or affect how a wave will travel. One, for example, one of the properties would be the forces between the molecules, because these forces would either would resist the motion up and down. Okay? Imagine if you were doing the wave at a sporting arena and you had a giant elastic attached to your butt. So as soon as you stood up, the elastic stretched and snapped you back down into your seat. Well, that would be sort of like the molecules or the particles having a force between them that attracts them. And if you tried to wiggle them, okay, so for instance, here's a string. If we're wiggling this string, well then we're trying to pull up on each piece of the string and make it go up. The forces between the molecules will resist us. And so if you had a very strong elastic in your seat, what would happen is you would be snapped back more quickly, or perhaps you would have a greater effect on the vibration that you have. But now imagine you have an elastic between you and the person beside you as well. Well, if you have an elastic between you and the person beside you, then it's going to be harder or easier for the person beside you to stand up and down because of the elastic that's pulling on you. So think about this. I realize now, forget about the elastic on the seat, because that's more about oscillation. Let's think about two people trying to do the wave with an elastic between them. If you try to stand up, right, and you're sitting in the chair, you will try to go upwards and put your arms up and yell, while your friend is sitting down. You're going to stretch the elastic between you. And so the amount of stretch then, that's what's causing your friend to suddenly spring upwards. That elastic is pulling on him as well. So the forces between the particles will affect how quickly the person beside you is yanked up out of their chair to keep the wave going. And as soon as they get yanked up out of their chair, they will be attached to another person. And as they go up, that elastic will pull on the next person. And this is how the wave travels through. Now in a sporting event, we do this with our brains. We just watch and try to get it right. But in a string, strings can't decide. They don't have a mind. So it's these elastical forces between the particles that actually cause the next part of the string to move. Okay? For humans at the ball game, this is a conscious awareness that pulls us or forces us to move. But think of it like elastics. So those forces between the particles have nothing to do with your wiggling or shaking. They have to do with the kind of molecules that are in the particles and how they're joined together. Okay? The other thing that matters is, and it's kind of related to this, so maybe I'll just put this as a sort of dot or dat. The density of an object then. Denser objects would have greater forces between them, pulling them in tighter. The tension could create a change in those forces between the particles. Heat causes a change in those forces between the particles, and so on. There are lots of different things that could change the relationship between the particles, or the forces between the particles in any object. And that's what the speed of propagation depends on, which means something kind of important and a little bit simpler. That is that under the same circumstances, if you don't change the heat and you don't change the tension, if you keep everything the same, speed of propagation of a wave speed of propagation of a wave in a particular medium. Remember, the word medium is what the wave is traveling through in a particular medium, remains constant, doesn't change. So let's think about a string. If I take a string like this, that's flat, and I wiggle it, I will produce a wave that travels down the string, and I'll just put it halfway for now. So it starts to go this way. After a certain time, it will get to the end of the string. Now, if I don't change the string, if I use the very same string, and I make a different wave in it, like this one, which has a different frequency, well, that wave will travel down as well. Or I could even make it a very, very, very fast vibration and make a wave that travels like this. Then this would travel down the string as well. What we're basically saying is, as long as the string hasn't changed in any way, if it's the same string under the same conditions, then all of these waves will reach the end of the string at the same time. Which means they all travel at the same speed. It doesn't matter how hard or how fast you wiggle the string. Okay? They all travel the same speed. That's what we mean by it being a constant in this particular medium. The wave will always end up at the same position at the same time, no matter what. So it is completely independent of the oscillation. That's what we're really trying to say here. I won't write that down, but you might want to write that down. The speed that the wave travels is completely independent of the oscillation, and is completely and utterly dependent upon the properties of the medium itself. Which means that as long as you don't change the medium, waves, no matter what frequency they are, or what their wavelength is, will all travel the same speed in that medium. Now, one last thing then. If all waves travel the same speed in a medium, and the speed is a constant, let's look at how we might be able to express this mathematically. Let's take the idea of frequency, which is cycles per second. We've learned that already. And remember, it's just a number on top. It's a counting number on top per second. Let's multiply that by a wavelength, which is simply how long a wave is, which is measured in meters. So I'll put these units in brackets. Well, what happens if we multiply cycles per second times wavelength? Well, then what we're actually doing is we're using this counter to count the number of meters that are happening every second, the number of meters of wavelength that go by every second. And meters per second is speed. So, if we count the number of
wavelengths that go by every second. We're effectively counting the distance of that repeating unit, and the distance of that unit every second is the speed. So it turns out that the speed of a wave is equal to the frequency times the wavelength. V equals f lambda. This is sometimes referred to as the universal wave equation. There are many types of wave equations, but this is the most basic, and it's the first one that we learn, and it's critically important. Now remember that the speed of a wave is constant. So that opens up the door for some very interesting things that happen. If the speed of a wave can never change, all right? So let's compare two speeds. I'll draw them in red and the same size to show that they don't change. I could get that speed by using a very large frequency with a very small wavelength. Or I could get the very same thing by using a very small frequency with a very large wavelength. Right? A big number times a small number produces the same product as a small number times a big number. And so what that means is that frequency and wavelength have a relationship with each other. If a frequency begins to get smaller, then the wavelength has to get bigger, right? If the frequency of a wave drops, then the wavelength of that wave must rise. This is an indirect correlation. One is going up, one is going down, right? And likewise, if the frequency of a wave begins to go up, then the wavelength must go down, because they have to always work out to the same speed, because the speed is constant, which is kind of an interesting thing. And we'll talk more about that and see more of how that happens down the road. So that's the speed of a wave and the universal wave equation. So we have frequency and period, which are really the same thing, but are sort of reciprocals of each other, different ways of looking at something. And then we had this idea of the speed of the propagation of a wave, how fast a wave will travel through a particular medium. And the speed of the wave depends upon the frequency and the wavelength. And they can be stated mathematically in this universal wave equation, which is for all waves. Universal means it works for all waves of any kind, any type. Remember, longitudinal waves are really transverse waves in disguise, so this all applies to both types of waves. All right. And so what this means, as a last thing, is that we can take the physical properties of different mediums and we can determine the speed that waves will travel through them. So, for example, which will introduce us into our next section, we're going to be looking at sound waves. Well, when sound waves travel, they can travel through all kinds of things. Typically, they travel through the air. Let's make a little chart. If sound travels, let's go medium and speed. A sound wave traveling in the air might travel somewhere around 340 meters per second. That's pretty fast. But for instance, a sound wave traveling through something like aluminum, a vibration caused by traveling through aluminum, might go 5,000 or more meters per second. I'm just guessing at these numbers. They're close, but they're not perfect. And so the speed of a sound wave in air will always travel this speed. It doesn't matter whether you yell really loud or you're really soft, whether you have a high voice or a small voice, whether it's the sound of a giant locomotive traveling by or the tiny flap of a butterfly's wings. All of those sounds will travel at the same speed through the air if the air remains constant. If the air doesn't get warmer or more humid, or the properties stay the same. Likewise, if you bang on a piece of aluminum, the sound of that, the little clinking noise you make, will travel through the aluminum at 5,000 meters per second or so, And it doesn't matter whether you bang it really hard, really soft, or make a loud or quiet noise, the speed through a particular medium will always be constant. And so as we begin to look at sound, which is the next sort of thing on our list, we'll start looking at, the different speeds at which sound travels. And that's it for today. So make sure you understand all of these concepts before we move into sound on Monday, because we need to have all this under our belts so that everything makes sense.